The first property we're going to prove concerns the modulus of z1 multiplied by z2. So to prove this property, we'll let z1 equal a plus bi and z2 equals c plus di. So Cartesian form, and we'll focus on the left hand side. And then expanding out z1 and z2, and then using FOIL to expand out the multiplication there. Now remembering that I squared equals minus 1. Next, we'll group our real parts together and the imaginary parts together, and then we apply the definition of modulus, and then carefully expand out both of those squares. And then we'll notice that the two middle terms cancel out, and we're left with a series of terms, a squared times c squared, etc. And we notice now that that can be factorised as a squared plus b squared multiplied by c squared plus d squared. And we separate out those two square roots, and we note that a squared plus b squared square root is the same as modulus of z1, the other one's modulus of z2, and we're done. The next property concerns the multiplication of cis theta 1 times cis theta 2. So focusing on the left hand side, we use the properties cis theta is cos theta plus I sin theta, and we use that property to expand out the two cis theta 1 cis theta 2 on the left hand side there, and then we expand that out using FOIL. Again, being careful to note that I squared equals minus 1. Group together the real parts and the imaginary parts. And notice now we've got identities that match our addition formulae for cosine and sine, as we've written down here. So using those properties now, we can replace the first bracketed term or expression by cos theta 1 plus theta 2, the second one by I sin theta 1 plus theta 2, and now we just use the definition of cis, and we've completed our proof. So the last property we're going to prove here relates to cis theta 1 divided by cis theta 2 equals cis theta 1 take cis theta 2. Focus on the left hand side. We multiply numerator and denominator by cis theta minus theta 2. And we do that because that allows us to simplify the denominator. Denominator simplifies down to cis 0 in this case. And we notice that this cis 0 is equal to, we see here, cis 0 is equal to cos 0 plus I sin 0. Cos 0 is 1, sin 0 is 0. So that cancels down to cis theta 1 take theta 2 over 1, which cancels to cis theta 1 take theta 2, which is what we're trying to prove.